This is a video that showcases the abilities of the Arduino prosthesis. The first part of the video goes through the design choices and parts that build the prosthesis. The second part of the video examines the electrical schematics and the usage of the MindWave Mobile. The final part is the actual demonstration of the usage of the Arduino prosthesis. These are fingertips. This is a finger segment, and that's a finger spring. These are the servo cables, and that's the thumb, which is perpendicular to the rest of the hand to aid in gripping. These are the finger hinges. They serve to both connect each of the finger segments individually, as well as enable the finger segments to bend into each other, providing a nice natural flex. This is the diagram of the artificial finger. The finger segments form the body of the finger. They house the steel cable on which the servo pulls to flex the finger, which itself terminates in the plastic fingertip. The compression spring in between each segment provides a restoring force. When the finger ceases to flex, it expands and forces each finger segment back into their unflexed state. A finger hinge connects each segment together, while enabling them to bend into each other. This image depicts the flex state of the artificial finger. Note how the trapezoidal shape of each segment enables them to fold cleanly into each other. This diagram depicts all 5 fingers in a fully unflexed state. The diagram is not fully representative of the thumb, however, which is actually placed perpendicular to the rest of the body. The small circle in the corner of the hand represents a pulley around which the thumb cable is wrapped to enable it to move. This diagram depicts all mechanical components of the arm. On the edge are the 5 fingers and the thumb pulley. In the center of the arm is the Futaba BLS155 servo mechanism and its servo horn, to which all the fingers are attached via their servo cables. When the servo rotates, its horn pulls the cables around the horn circumference. As the cables are pulled, they pull the fingers with them, causing the fingers to follow the path of least resistance and flex inwards. This diagram depicts the design of the elbow mechanism. The base of the elbow is made of PVC plastic. It is connected to the Dynamixel MX64 servo motor via a modified PVC plug that acts as a servo adapter. A metallic bracket is attached to the servo motor. When the servo spins, it actually rotates the bracket up to 270 degrees around it. An M8 screw connects the servo bracket to the hand bracket. The hand bracket is designed to hold the arm and hand in place while providing a method of flexing the two around an elbow. The bracket is shaped like a tuning fork to provide stability and reinforce the arm. One arm of the tuning fork is shorter to accommodate to the hand servo's horn. The hand and arm acrylic plastic are actually fitted into slots within the bracket. They are then secured by adhesives, providing the arm with a way of connecting to the elbow servo. The elbow servo rotates its bracket, which rotates the arm bracket via the M8 screw, which in turn rotates the hand and arm, which are secured to it. This is the BlueSmurf harness. The BlueSmurf harness helps to secure the BlueSmurf Silver into place, as well as keeping it from touching any of the other electronics. The BlueSmurf Silver is a Bluetooth modem that serves as the method of communication between the Arduino Mega and the MindWave Mobile. The Arduino Mega is a microcontroller that controls the entire apparatus. It's wired to both the BlueSmurf Silver to receive data, as well as to both of the servo motors to transmit controlling information to them. This is the Futaba BLS155 brushless servo. This servo controls the fingers of the hand by pulling on its servo horn, which tugs the cables and then pulls the fingers. This is the arm bracket of the hand. The arm bracket secures the hand in place, as well as providing an easy, simple method for the Dynamixel servo, which controls the elbow in order to move the arm. These are the wires for the servos that connect to their power supplies. Here we see the electrical schematic at the heart of the Arduino prosthesis. The Arduino Mega serves as the linchpin of the design. It receives brainwave data from the MindWave Mobile via BlueSmurf and then interprets and aggregates that data into focus and relaxation values. Using those values, it controls the Futaba and Dynamixel servo motors. 2 dedicated power supplies power those servo motors, while the Arduino powers the BlueSmurf and acts as a common ground for said servos. The Arduino itself can receive power from either a 9-volt battery or a computer power supply. This is a visual overview of the entire operating procedure of the Arduino prosthesis. The MindWave Mobile registers the user's brainwaves and sends them via Bluetooth to the BlueSmurf Silver. The blue Smurf silver then transmits the data from the mind wave to the Arduino Mega. The Arduino Mega takes that mind wave data, aggregates it into focus and relaxation, and uses those two values to control the servos. The servo motors in turn then control the fingers and the elbow. This next clip will demonstrate the use of the MindWave Mobile to record and display the user's brainwaves in a graphical interface. An inset in the corner of the screen displays this graphical interface. In the upper half of the inset, the individual readings of alpha, beta, gamma, delta, and theta brainwaves are displayed in the radial plot. In the lower half of the inset, the aggregated values of focus and relaxation are displayed in the form of radio dials. The bar graph in the upper right shows a generalized EEG signal as well as the real-time bar graphs of the individual brainwaves. This clip will be demonstrating the output of the MindWave Mobile as interpreted by the Arduino Mega. The inset in the top left shows the Arduino's interpretation. It collects the brainwave data and aggregates that data into two values of focus and relaxation. Because only two forms of control, both with easily understood connotations, are used, it requires almost no training for the Arduino prosthesis to be swiftly and easily controlled. This clip shows the Arduino Mega using the brainwave data to control the Arduino prosthesis. There are two threshold values used by the Arduino Mega, one for focus and the other for relaxation. For the purposes of this demo, both threshold values are set to 50. When the user's focus value exceeds 50, the Arduino directs the finger servo to move and flex the fingers. When the user's relaxation exceeds 50, the Arduino directs the elbow servo to move and thus rotate the elbow. In this clip, other individuals test out the Arduino prosthesis. Their testing of the device showcases the universal adaptability of the prosthesis, as the user in this demo is trying the prosthesis out for the very first time. His swift execution of both the finger bending and the elbow rotation illustrates the ease of use which other users will have with the Arduino prosthesis. This concludes the presentation video of the Arduino prosthesis. 8 months of work went into the construction of this device, and the video details the end results of the work. Thank you for watching.